and I am going to be walking through what is required for Unit 3 in AP Chemistry. Unit 3 is on intermolecular forces and their properties. So the 5 main points of this is we have our intermolecular forces, which we would like to call IMF. And then we have our solids, liquids, and gases. And how do we determine their properties based on their IMF? So the IMF connecting into those. Then we have kinetic molecular theory, which is our KMT of gases. It mostly deals with gases. It is also talking about solids and liquids as well. And then how molecular interactions in solutions and mixtures. And then the photoelectric effect, which I am not going to cover very much at all. All right, intermolecular forces, IMF. How do we feel about that? So that we have these 4 fundamental IMF forces. And you should understand that. We have LDFs, London dispersion force. We have dipole-dipole forces and ion dipole forces and H bonds. Okay. The London dispersion forces, these increase for larger atoms and for more spread out molecules. So London dispersion forces, if we remember correctly, you would have a center, you would have an atom and another atom, that molecule or atom, it could be a molecule, that have these electron clouds around them. And as the core, this looks like 2 eyeballs, doesn't it? The core of the atoms are positive and the electron clouds are negative. And depending upon how these things oscillate, there is some attraction between these two because the positive core attracts the electron cloud from the other side. And the positive core of one attracts the electron cloud. And as these electron clouds get dispersed, let's say they get shifted a little bit this way, then there is a more attraction towards it. The more electron clouds can disperse and move and get rearranged, the stronger the LDF is. So it's between all molecules. Every atom, every 2 molecules or every 2 atoms that are attracted to each other have London dispersion forces, but it's a very weak force. And then the next one is the dipole-dipole forces, and these are between polar bonds. So dipole, think of polar, where you have a positive and negative side, and you would have these attractions between these things. So if I were to look at my dipole forces, I have a positive and a negative side of one molecule, and I have a positive and negative side of the other molecule, and they're attracted to each other because of this. So this is stronger than LDF, but still weaker. If the molecules are big enough, though, LDF could be stronger than dipole-dipole. Next is our ion dipole. We have ion dipole. A great example of that would be ions like, say, salt water. You have your ion and you have your water molecule. You should know water molecule very well. It has a partial negative side and it has a partial positive side. The oxygen molecule is the negative, the hydrogens are the positive, and there is an attraction between the ion and the polar molecule. Dipole is polar molecule. And finally, we got, water is kind of going to also be an H bond. So finally, we have our H bonds, which is between when you have H connected to N, O, or F. Very common one is water. We're going to use water here. We have our H's here. If the H, because this is so strongly polar and a lot of electrons are pulled to the O, if you look at a second water molecule, if the H is attached to an O, N, or F, then there is this very strong dipole force, a hydrogen bond force that is there. Hydrogen bonds are the strongest, London dispersion are the weakest, and this is about the right order. All right, so with the IMFs, if you understand about IMFs, then they can explain some of these properties. These are the properties that you should be able to explain: boiling point, melting point, vapor pressure, viscosity. Okay, boiling point and melting point are essentially the same thing. So you need a higher boiling point if your IMFs are strong. If you have a strong IMF, then you need a high boiling. You're going to have a high boiling point or a high melting point. Stronger the IMF, the higher the boiling point. The weaker the IMF, the lower the boiling point. So you can predict based on their IMF. If you're trying to compare two molecules, which one has more IMF? That's the one that's going to have the higher melting or boiling point. Vapor pressure is this idea of a liquid that is going to be released. Let's say we have a beaker. Inside of that beaker, we have a liquid. That liquid is going to produce gas molecules because of evaporation. The weaker the IMF, the more vapor pressure. So if your vapor pressure is high, then it means that you have a low IMF. So it has the opposite interaction between that. And then viscosity is how it flows. Highly viscous liquids are slow flowing and they have a large IMF. And then we have these. So how do the different things compare? And then we have the distinguishing between the different kinds of solid. Network solids are like diamonds, where there's an interaction of covalent bonds between all of these things. This is not IMF. This is all covalent. So a network solid is all covalent. Now in a covalent, all right. In the molecular solids, like sugar, this is where we're going to have, the molecule is covalent bonded, but the solid is IMF bonded. Usually, if it's sugar, that's a dipole, and you would have all of that. Let's give that a different color, red. Okay, so that is our molecular solid. And then metallic solids, there's metallic bonds between them. They're not covalent, they're not ionic, they're not even IMF, but it's the sea of electrons that hold onto those. But making sure to know the difference between those different types of properties of solid. Then we have the topic of solids, liquids, and gases, and being able to distinguish what is going to, what's their behavior like. So how do they move? Their molecular movement. In a solid, they vibrate. In a liquid, they are attracted to each other strongly, but they move around. In a gas, they are free and have very low IMF. And then what they're arranged like. In a solid crystal, there is a very ordered structure. In a liquid, it's close, but there's no real order to the structure. And in gas, it's all random. And then KMT of gases emphasizing collisions, just to make sure that we get this idea of randomly moving particles with a very little IMF and causing collisions with that. More about KMT here in a second. All right. So now we are going to focus on gases. In a gas, you need to know the ideal gas law. Do you know that? You should know that by heart right now. Let's see if you said it already before I did, but it is P times V equals N RT. You should know all of those. I would have the value for R written down, and that everything P, usually in atmospheres, V is in liters or milliliters, N is in moles, R 8.0. Oh boy, I'm drawing a blank with what that is, and temperature in Kelvin. Partial pressure. This is the idea that the pressure is total is going to be the sum of all the different pressures. If you have molecule A and you have molecule B and you have molecule C, all of them mixed together, the overall pressure of the whole thing is that. This often comes into play when we talk about water, doing an experiment over water. You may be making a gas, let's say make chlorine gas, but you're doing it over water, so there's going to be some water vapor as well, and you have to know the vapor pressure of that to know what the pressure total is in the gas. The different, being able to graph different laws when you're looking at a comparison between things. So what this is asking here is if we compare, for example, the pressure versus volume, what is that going to look like? That is going to be an inverse relationship. So it should look like this. If we do a different thing, like say we did pressure versus number of particles. Well, the more particles that we have, then the P versus V is, so actually let me do this because I have it up here. I'm going to do temperature instead. The higher the temperature, the more the pressure is going to be, and this is a direct or linear relationship. P versus T is inverse. So that's the graphing, being able to notice all those. I would have all of the laws written down someplace that we have gone through in class. KMT, kinetic molecular theory for gases, being able to describe it. There's many parts to this. Molecules are moving randomly. Some molecules are moving faster, some are moving slower. They have very little IMFs. They collide into each other, causing pressure. So that's all kinetic molecular theory. The Maxwell-Boltzmann distribution. Let's see, I don't have that written down here. So the Maxwell-Boltzmann distribution is this idea when you look at, I thought I had this charted out. If you're looking at the energy, the kinetic energy of the particles, which is related to their speed, versus the number of particles at a given temperature, you get this distribution that looks, I'm doing a very bad job of drawing this. It should be a little bit more curvy at the top. So you get this kind of distribution that looks like this with this long tail. This is saying that there are some molecules that have low kinetic energy. There's a lot of molecules that have the average kinetic energy. So there's a lot of them that have the average kinetic energy. And then there are even some that have more kinetic energy than you know. The average kinetic energy is your temperature. But there are some molecules that are moving faster and some molecules that are moving slower. And it's, for example, it's the faster ones that are going to evaporate out of the surface. It's the slower molecules that are going to condense. But on average, maybe they are either going to be a liquid or a gas. And so you would have the kinetic molecular theory has to do with at a given temperature, you have this distribution. A bigger atom, a heavier atom or molecule, is going to be the number of molecules you're going to have. You know what? I have these switched. So sorry about that. We should, the normal way of representing this is your kinetic energy is on the bottom and your number of particles is on the top. So as you get higher and higher kinetic energies, then you get a certain number of particles. The most is around where your average are, but slower or faster, then you can have those in that direction. All right, distinguish between temperature, kinetic energy, average kinetic energy, and the kinetic energy of an individual molecule. So temperature is average kinetic energy if you're using the Kelvin scale. The kinetic energy of an individual molecule is somewhere on this curve, and it's not necessarily corresponds directly to the temperature. And so individual molecules can have different temperatures. On average, they are going to have the temperature. If you add up all of the energies, that's going to be the total amount of energy, which is not the temperature either. So that depends on how many molecules you have. All right, kinetic molecular theory. Deviations from the ideal gas law. Distinguish between ideal gases and less than ideal gases. So a less than ideal gas, you are going to have IMF forces. And so they are not going to be there. And your volume of the actual gas molecules does not equal zero. So some of the assumptions that you use in an ideal gas is that there is no IMF. And you also assume that the volume of the ideal gas is essentially zero. The actual molecules have zero volume compared to the size of the container. Less than ideal is not that case. What situations are they going to act less than ideal? Well, if you have a high pressure, then it's not going to, their molecules are really pushed towards each other, and you're going to get this effect of IMF, or they could be really close to each other, and so the volume isn't really zero because they're so close to each other. And the other case is when you have low temperature. If they have high temperature, they're cruising around so fast that they're acting ideal. But at lower temperatures, they're going slow enough that IMF and volume start to take into effect. So high pressure and low temperature. Finally, solutions and mixtures. So homogeneous mixture equals solution. So those are the same thing. Describe what those are like. You may have to describe how ions get dissolved in water. What is that? What is a dissolving process, and how the water molecules go around each of the individual ions or polar molecules. For that, molarity, you should know that molarity equals your moles per liter. Moles, how many moles of your solute, what gets dissolved over how many liters in the solution. All right, representation of solution. These are the drawings. So be able to draw ions in water. Be able to draw polar molecules in water. Dipole equals polar. You can and then draw the process of water dissolving. So represent the solutions by how you draw them. And then separation of solutions and mixtures and chromatography. We didn't talk a lot about these things. Filtration. It happens when that's a way of separating things, but this does nothing to a solution. So it does not separate a solution, but if you had a suspension, you could take out, for example, sand out of water by using filtration, but the sand was not truly dissolved, and so it doesn't work for a solution. Distillation is when you boil something away, and this does work for a solution. Check. And chromatography also separates a solution. I'll talk about chromatography here in just a second. But distillation, let me go down here to distillation. You can distill things by taking the water out of the solution and be left with the stuff that's dissolved in the water, and the water becomes pure. But you could also, if you say had a bunch of hydrocarbons that were all different weighted liquids mixed together, you could potentially distill each one of those things. Like, let's say you would have alcohols. You can distill different alcohols from each other, or take the water out of the alcohol and you get pure alcohol or pure water. So you can distill those things, or you can distill petroleum by taking out different hydrocarbons, because each hydrocarbon has a different density and mass, and so you can do that, and it's all by boiling it away. All right, chromatography. So chromatography is using paper chromatography. Would be if you have a solution that has a bunch of different molecules in it. let's say some are blue molecules and some are red molecules. Because they're in the liquid and they are sitting in there, if you were to put a piece of paper, let me get a piece of paper. Here's a piece of paper. And I put that in here, it's going to soak up these different molecules. So what happens is the blue molecules may rise, and they rise to a certain level. And then the red molecules also rise, but they rise to a different level. We have separated the blue from the red. The paper is the stationary phase. The mobile phase is the dyes that may be like in a pen or something like that. And they move through there. The reason why the reds move up higher may be because of their mass and because of how they attract to the pieces of paper, and so they can climb up the paper using capillary effect and those things. And so some molecules will do better at that than others, and so you have to have the right kind of material to do that. So that is another separation technique, is chromatography. All right, solubility, describe solubility. Solubility is how much can dissolve. And it depends on the properties. So you need to, like dissolves like. And we know that polar dissolves polar, like water dissolves sugar. Or nonpolar dissolves nonpolar. And so the type of molecule that there is will depend on that. Now, ionic substances dissolve in polar as well, and so how much can dissolve depends on that. So it all relates to IMF as well. Finally, a couple things that we aren't covering. I'll just mention these really quickly. So if you took spectroscopy and electromagnetic spectrum, if you have, I'm going to take an atom and we're going to put electrons around it, okay, in different energy levels. And you could also take a molecule that is connected to another molecule and has a bond to it, okay. So the vibration of particles causes light. So if the electron were to jump up and down in between energy levels, when it drops down, it will emit a radiation of light. Electron's really small, and it can emit something that's in the visible spectrum. You get this. But you could also have two atoms or ions that are connected to each other, and they vibrate with each other. Just because there is this molecule, think of the bond like a spring, and the tighter the bond, the faster they're going to vibrate back and forth. They're just going to shake. If it's a looser bond, they're going to shake more loosely. Depending upon what they do, they can let off they can let off light. Or they could, if it's a slow bond, maybe they're going to let off a slower frequency of light, depending upon that. So the electromagnetic spectrum is what they let off. And the electromagnetic spectrum can range from your microwaves to your infrared to Roy G. Biv, which is your visible spectrum, and then you can go to ultraviolet, and you can even go higher than that, okay? So weaker bonds are going to give more microwave radiation. Stronger bonds are going to do that. Electrons tend to be in this Roy G. Biv area. Okay, that's spectroscopy and the electromagnetic spectrum. Photoelectric effect is kind of similar. If you have a molecule, let's say a piece of metal, and you have electrons on it, and there's a certain bonding energy to those electrons, and you hit it with some light, so this is the opposite effect, that electron can get knocked off if the frequency of the light matches the vibration of the electron on the atom. So depending upon the energy that electron has is what that's going to do. All right, and then finally, Beer-Lambert law. Hopefully you know Beer's law. It's the ABC law. And we did so many experiments on this. Absorbance equals your absorptivity constant times B, which is your cuvette length, and C, which is the concentration. So be able to explain a calibration curve. We made some of those where we have absorbance and we have concentration, and we do our little line there, and we get a trend line that goes through it, and that trend line tells us how the absorbance and the concentration match each other. Okay, so at different concentrations, we get different those. The slope of that line is the absorptivity constant. Hopefully, you remember all those. Be able to use this curve for Beer-Lambert law. Be able to use Beer's Lambert law. And that's it.